All right, good afternoon, everyone. Let's start our lecture for today on conduction and convection. So it's still continuing from what we've been learning so far in terms of temperature and internal energy. So we've already defined what temperature is, both in the macroscopic perception of hotness or coldness of the object and microscopic kinetic energy of the moving particles. And yesterday, in the lecture yesterday, we learned what heat is. We defined what heat is, and we've learned that heat is internal energy that's transferred from a hot object to a cold object. And we learned the two kinds of heat: sensible heat, where the heat transferred results to a change in temperature, or we learned also that the heat transferred can result to a phase change. So we've learned how to calculate the amount of heat, but we haven't yet discussed how heat or how energy is transferred in the first place. So in today's lecture, we will see we will start the discussion on the different heat transfer mechanisms, how heat is transferred from hot to cold objects. In this course, we will consider three mechanisms of heat transfer. In today's lecture, we will learn about the first two, conduction and convection. And in tomorrow's lecture, we will learn the third mechanism, which is radiation. So just a few concepts to keep in mind as we learn the different heat transfer mechanisms. Heat is only transferred if there is a difference in temperature, right? If there are two objects, one of which is hotter or at a higher temperature to another object, that's when heat transfer occurs. If you have two objects at the same temperature, then those objects are at thermal equilibrium and heat is not transferred between them. The direction of heat transfer is always from high temperature to low temperature objects or regions. Right, okay, so let's start with the first mechanism, which is conduction. This video will show us a visualization of heat transfer by conduction. Notice how there's a flame, and there's a spoon placed in front of the flame. There are paper clips glued onto the spoon. Notice how the spoon, it takes time for heat to be conducted from this part of the spoon to the other end. And that's why the paper clips fall one by one in sequence. They don't all fall at the same time. The clips are, by the way, glued by wax. And so we can see there that the spoon heats up first closest to the flame, and as heat sort of propagates from this end. As it propagates from the end of the flame, the wax closest melts, causing the paper clip to fall, of course, and then the next paper clip falls as heat melts the wax. So we can see here that heat transfer by conduction takes time to go from one end to the other end. The other thing to note here is that in heat transfer by conduction, energy is transferred, or energy or heat is transferred by direct contact. So there needs to be direct contact between the colder object and the hotter object for heat to flow. We cannot see macroscopically, we cannot really observe macroscopically how heat is transferred from this end of the spoon to the other end. We need to look at what's happening microscopically to understand heat transfer by conduction. But the heat is transferred within the material itself. There is no movement involved. So if we look at the microscopic composition of the spoon, say for example, the spoon is made up of atoms. Right? So as the atoms closest to the flame heat up, they absorb energy from the flame, and we've been learning this already for how many lectures now. When the atoms acquire energy from the flame, the atoms vibrate. Right? High temperature means faster vibration of the atoms. And as the atoms vibrate, they collide with neighboring atoms. When they collide with neighboring atoms, they share some of the energy, and that causes the neighboring atoms to vibrate themselves. And the neighboring atoms, which started to vibrate again, collide with neighboring atoms, and therefore sharing some of the energy. So that's, in essence, the energy propagates from the point closest to the flame to the point farthest to the flame through the vibration and collisions of atoms. This is a good illustration. This animated GIF is a good illustration of sort of what's happening to the atoms. Notice how the atoms closest to the flame vibrate first, then they collide with neighboring atoms, sharing the energy with them, and the collision is progressive until the whole material has the same temperature and all the atoms are vibrating with the same average kinetic energy, so that the temperature of the object is homogeneous. Okay, so this is how conduction, heat or energy is transferred by conduction. Any question about the mechanism for conduction? Or I hope it's relatively clear, quite straightforward. Yeah, just two things to remember: heat transfer by conduction, the two objects need to be in contact, and heat transfer occurs microscopically via the vibration of atoms. So depending on how easily heat or energy, when I say heat, I'm referring to energy. So depending on how easily heat or energy is transferred by conduction, we can classify materials into two. First, we can classify them as thermal conductors, in which case we say they're thermal conductors if their thermal conductivity K is high. A high thermal conductivity K means that heat or energy is transferred at a faster rate. So intuitively or based from experience, we know that metals, they're good thermal conductors. The second kind of materials we can classify materials into are thermal insulators. For thermal insulators, they conduct heat slower compared to thermal conductors, and that's because thermal insulators have a low thermal conductivity. So thermal conductivity determines the rates of conduction, or rate of, meaning how fast energy is transferred by conduction. All right. Good. So we've learned how heat is transferred by conduction and the property of the material that determines how fast energy is transferred by conduction. And now let's look at this, just this conceptual example to sort of emphasize what heat transfer by conduction is. So given your experience of what feels colder when you walk on it, which of the following surfaces given here, A, B, C, would have the highest thermal conductivity? A rug, steel surface, or concrete floor? Which surface would you feel colder when you step on that surface, in other words? Steel, right? I mean, we all know the purpose of the rug is to make the floor warmer. So obviously, you don't feel so cold stepping on rug. Steel does make you feel colder, and that's because the higher the thermal conductivity of the material is, the bigger the heat loss. Yeah, thermal conductivity gives you the rate of heat transfer, or how fast heat is transferred by this material. So if steel has the highest thermal conductivity, then it would conduct heat or energy faster than the other materials, and that results to a bigger heat loss. And the more heat we lose, the colder we feel. Okay. Right. Cold is, of course, perception of temperature. So the colder we feel, the bigger the change in temperature that we experience, right? And that's because we cool down. In fact, if you look up in the table the thermal conductivities of these three materials, thermal conductivity is a property of the material, which you can look up at some in some table. If we compare the thermal conductivities of steel, concrete, human tissue, and wool, wool of course makes up the rub, then we'll see that steel has indeed the highest thermal conductivity. Okay. It then facilitates faster heat transfer and therefore bigger heat loss. All right, clear enough? Good. All right, so then let's look at how we can quantify the amount of heat or energy that can be transferred by conduction. So in this picture, we can see a hot slab and a cold slab. These two slabs are connected via this duct. Okay, we have a difference in temperature. So we've learned that if you have a difference in temperature, energy will flow. Energy flows from hot to cold. So there is energy flow from the hot slab to the cold slab. Now, how do we quantify how much energy Q is transferred from the hot slab to the cold slab? If we think about it intuitively, it should depend on the thermal conductivity K. As we've been discussing in the previous slides, the bigger the thermal conductivity, the more energy is transferred, because you have a faster transfer of energy, the higher the thermal conductivity K. The amount of energy transferred also depends on the area that's in contact. Okay, so let me clarify what this area means. So of course, this hot slab has some area A. Likewise, this cold slab has some area A cold. But what's important is not the actual areas of the hot or cold objects, but rather it's the area through which energy is transferred, right? Because it's only through this area where the two objects are in direct contact with each other that energy can transfer through conduction. So it's this area, the cross-section, the area connecting these two objects, that's important. Right.
So it's cross-sectional.
Yeah, in this case, it's the cross-sectional area. It's not always the cross-sectional area. It can be the surface area. Say there's the example we'll look at, we'll use surface area. So say I have my skin is in direct contact with the steel here, then how much area is in contact with the steel post will be what's important. Yeah, it's not always cross-sectional area. Right. So the amount of heat transferred Q will also depend on the temperature difference between the two objects. Okay. So delta T here, it's not the change in temperature that we've seen yesterday, rather it's the difference in temperature. because I mentioned earlier that heat transfer only occurs if there's a difference in temperature, right? So how big the difference is will influence the amount of heat transferred between the hot and cold objects. Right, the amount of heat transferred also depends on the time. So T here is the time of heat transfer. Of course, the longer it is that these two objects are in contact, then the more heat is transferred between them, right? Okay. If I touch this cold metal surface and right away remove my hand, then the heat transferred will be less compared to when I touch my skin for a longer time with the cold surface. So the amount of heat will also be proportional to the time. And finally, the last influencing variable to the amount of heat is the length or the distance over which heat will need to travel or propagate for it to transfer. So it's inversely proportional because the longer the energy needs to travel, the smaller the amount of energy is transferred. So does this equation make sense? Right? Amount of heat transferred by conduction. Okay. And knowing what each of these variables mean is quite important. Sometimes we also want to know the rates of heat transfer. Sometimes we want to know not the exact amount of heat, but rather how quickly heat is transferred between the two objects, in which case we want to consider the rate of heat transfer. When we say rate, it's always something divided by time. In the case of heat transfer, rate means it's the amount of heat divided by time. So it's still heat transfer by conduction. So it still takes the form of the equation we've seen in the previous slide, except that instead of having time here in the numerator beside delta T, time is transferred to the denominator of Q on the other side of the equation. That then gives us the rate Q over T. Right, so rate Q over T, if we do dimensional analysis to look at the units, the unit for Q is joules because Q is energy. The unit for time is seconds. So joules per second, we've already encountered this. This is power, which is measured in watts. So rate is measured in watts, whereas amount of heat Q is measured in joules. But still, it's the same equation. Delta T here is still the difference in temperature or temperature difference. Okay. Hot minus cold. All right. Okay, so now let's look at an example.
When L comes down to zero, because then it goes
Infinite.
Heat transfer.
Yeah, infinite amount of heat transfer. That means heat transfer happens very, very quickly. In reality, it doesn't really. But also in reality, L will not go to zero. It will be still some small amount. Yeah. Okay, so let's look at this example. We have here as chicken eggs. They must be kept at 38 degrees Celsius for it to hatch. Given that the thermal conductivity of an eggshell is given here in the units watts per meter per Kelvin, and the average surface area of an egg is given in meters squared. The eggshell has a thickness given in meters. We want to calculate how much heat is lost if the egg is left for half an hour on a 24 degrees Celsius day. Right, so sort of you have that egg. Right. I'm drawing how thick the eggshell is quite exaggeratingly. So, you have the egg, the thickness of the eggshell. Right. The egg needs to be kept at 38 degrees Celsius. The outside temperature, 24 degrees Celsius. So it's a 24 degrees Celsius day. So we assume that the air molecules surrounding the egg will have a temperature of 24 degrees Celsius.
Think L should be 0.005.
Oh, 0.005. Yes, you're right. I looked at the wrong number, sorry. 0.005 meters. And right, so the picture here sort of just shows that it's like the top part of the egg that's exposed to the air. So let's just assume it's like that, but the total area exposed to the air is 0.011 meters squared. So that's sort of the scenario with the egg. Right, we're given the thermal conductivity of the eggshell. So it would just be a straightforward, because we know heat transfer by conduction. It's heat transfer by conduction because you have the egg that's directly exposed to the surrounding air. So there's conduction going on across the eggshell. So effectively, the distance for heat to travel is the thickness of the eggshell. Heat will be lost throughout the surface area of the exposed eggshell. So heat transfer by conduction requires K. K is watts per meter squared, or effectively joules per second. This is the same as watts. Okay. Times the area, which is given difference in temperature, 14 Kelvin. So this is T hot minus T cold. 38 minus 24 will be 14 degrees Celsius, but we learned that if you're getting temperature difference, the temperature difference in degrees Celsius will be equal to Kelvin. Just change the unit. Don't have to add 273. So the temperature difference will be 14 kelvins. Why I use kelvins for temperature? It's because the unit in the constant thermal conductivity is given in Kelvin. So I just want to be consistent with my units. Likewise for the time. So time is half an hour. I convert that to seconds because the unit for watts is joules per second, which requires the time to be in seconds. Divide everything by the thickness of the eggshell, and you get this amount. So over half an hour, the egg loses 24,948 joules of energy. Right, pretty straightforward, I hope. Okay, now there's a follow-up question. So over the same time, also over half an hour, calculate the associated temperature drop for the egg if the mass of the egg, the average mass of, if the mass of the egg is 57 grams, and the specific heat capacity of the egg is given here in kilojoules. Okay. So that's 37,000 joules per kilogram per Kelvin. Right, so how do we calculate the temperature drop? So we know the egg will lose from the previous slides or from the previous problem. The egg will lose 24,948 joules over half an hour. Okay. The energy lost will result, so this is the energy lost Q, will result to a drop in temperature delta T. We learned yesterday that if energy is lost, then that could result to a change in temperature delta T, right? Or a phase change. But in this case, the egg won't really undergo phase change, but it will undergo a change in temperature. Okay. So the change in temperature, which is the temperature drop we want to find, will be the amount of heat that is lost over half an hour divided by the mass of the egg times the specific heat of the egg. We've calculated how much energy the egg will lose over half an hour. The mass of the egg is given and the specific heat is given. Just be careful. If the unit is kilojoules, make sure to expand that to 2,000. 37 kilojoules, expand that to 37,000. 12 Kelvin, or this will also be equal to 12 degrees Celsius, because again, we're getting difference in temperature, change in temperature. Good. All right, so it's quite important to know the meaning of delta T in the equations, because so far we have encountered two equations for Q. One equation yesterday, Q equals MC delta T, and today's equation on heat transfer, Q having delta T as well. So Q equals MC delta T refers to the change in temperature, right? As a result of heat being transferred from hot to cold objects, their temperature will change. Okay? Whereas for the heat transfer by conduction equation, this delta T refers to a temperature difference, because you will only have heat transfer if you have a difference in temperature between two objects. Okay? So interpreting delta T is quite different based on which equation you're using. Good.
We're doing this calculation for an hour. The first calculation would say that we'd lose more heat, that would go below the temperature of the outside. So we wouldn't actually lose as much heat as we calculate.
No, you will only lose as much heat as to bring the temperature into equilibrium. Once you are at equal temperature, heat transfer stops. And so, yeah, you won't lose any more heat. Good. All right, so those are the important bits for heat transfer by conduction, but I'll just define what thermal resistance is. Thermal resistance is essentially the inverse of thermal conductivity. So this is thermal conductivity, right, that we've seen earlier. It's just that sometimes in the industry, they refer to thermal resistance more often rather than thermal conductivity. But thermal resistance is just the inverse of thermal conductivity. L is again defined similarly, the same way as before. It's the distance over which heat transfer occurs. So in terms of thermal resistance R, we can rewrite the rate of heat loss by conduction as this equation. Instead of K over L, we have 1 over R. All right, any more questions about thermal conduction? I mean, heat transfer by conduction before we move on to heat transfer by convection. Good. All right. So heat transfer by convection, this is the kind of heat transfer that involves the mass movement of the fluids, of liquid or gas, the particles or molecules making up the liquid or gas. Remember that in conduction, the object does not really move. It's just the vibration of the atoms inside the object. Whereas heat transfer by convection, there is an actual mass movement of particles making up the liquid or gas. So an example is boiling or heating up water, how heat is transferred from the bottom of the pot to the top of the pot. Of course, the bottom part will heat up first. Okay, when water heats up here, the water will expand, right? We've been learning that when objects increase their temperature, they tend to expand. When they expand, the volume will increase. So let me write that here. Density equals mass over volume. So the water molecules at the bottom of the pot closest to the flame, they will expand as a result of their increase in temperature. When they expand, their volume increases, therefore their density decreases. As their density decreases, they rise up to the surface of the pot. Okay. The colder water molecules will, of course, be more dense than the hot or warmer water molecules, so the colder water molecules will sink to the bottom. So, and that cycle continues until the temperature of all the water inside the pot is at equilibrium, at which case, when temperature is the same all throughout, heat transfer stops, as the same way as in conduction. Right. So there is really an actual movement of particles in heat transfer by convection. Right. So between the flame and the pots, of course, this one will be heat transfer by conduction, but within the pots, with the water molecules, it's heat transfer by convection. Similarly, this animated figure here shows you the heat transfer by convection of warm air closest to a heater or a heating source. So the heater will heat up the air molecules closest to it. The air molecules will tend to become less dense, so they rise up and they also circulate around the room. And that's how they bring energy or heat throughout the room. The colder air particles tend to sink because of the difference in densities of warmer and colder air. Right, so in these two examples of heat transfer by convection, there is actual movement, mass movement of particles, but the circulation of the particles is due to the differences in densities or changes in densities. And we call that kind of convection natural convection. So natural convection occurs naturally because of differences in densities, but we can also force We can also force the movement of air molecules or water molecules by forced convection. For example, if we use a fan, then the wind from the fan will blow the air particles everywhere in the room. So using a fan would give an example for forced convection. But the distinguishing feature of convection is the actual movement of particles. And as particles move, they bring with them energy, and therefore changing the temperature of the surrounding air particles or water molecules. Right. Any questions about the concept of convection? Is it clear the difference between conduction and convection? Yeah. I hope that's okay. So for finding the amount of heat transferred by convection, we can analyze this similarly to how we did in heat transfer by conduction. So the amount of heat is equal to this Q. Q is a property called the convective heat transfer coefficient or film coefficient. Yeah. I think in second year food tech physics, they use the term film coefficient, but in physics textbooks, they usually use convective heat transfer coefficient. So that's that Q there. A, it's the area over which the particles move about, or over which heat is being transferred. Delta T, again, this is the difference in temperature, hot minus cold temperature, because you have heat transfer only if there's a difference in temperature, and small t is the time over which heat is transferred. Okay. And similarly for the rate, if you want to find the rate, it's again the amount of heat transferred divided by time. Whenever we say rate, it's divided by time. So it's the same equation, except that the variable small t, time, goes into the denominator of Q. But still, Q times A times delta T is the same Q, A, and delta T as in the amount of heat transferred. Right? Easy peasy. I like this topic because it's quite easy. It's quite intuitive. So hopefully you also find it that way. So let's look at this example. So emperor penguins, they live in Antarctica, very, very cold, extreme conditions. They usually tuck their flippers close to their bodies, where the temperature of their skin is 35 degrees Celsius. And they do that, they tuck their flippers to avoid heat loss by wind, wind blowing over the flippers. So what we want to calculate is the rate of heat loss by convection through the flippers if they are not tucked in a windy day such that the temperature is negative 20 degrees Celsius. The flipper surface area is 0.05 meters squared, and the heat transfer coefficient, so that's is given here. So that's Q. Q is given. Right. The body temperature of the penguin is hotter than the temperature of the wind, the atmosphere, and we're given the area A. And what we want to find is rate. So you'll notice that we were not given any time value. And that's okay, that's fine, because we don't really need time. What we want to calculate is the rate, or Q over T. So we really don't need a specific time over which we want to find the amount of heat transferred. Rather, we want to find the rate, how much heat is transferred per unit time. All right, so some things to note here. Let me see if I have space to write on here. I'm a terrible drawer, so I'll just draw the penguin as maybe the foot and flippers like this. Okay, so of course the penguin, all of its skin is exposed to the atmosphere, right? So there will be heat loss all throughout the exposed surface area of the penguin's body, right? But what we are only, and if you want to find the total heat loss by the penguin, we do have to take into account the total surface area that's exposed to the wind. But what we are only after here is the rate of heat loss through the flippers in case they're not tucked in. So it's just the rate. So if wind blows over the flippers that are not tucked in, wind will carry away energy from the surface of the flipper skin, right? And this is why it's heat transfer by convection, because you have wind blowing over the flippers, and the blowing wind sort of is a mass movement of air particles that take away heat from the flippers, right? There is also heat loss by conduction, because as we've seen in the example of the egg was just sitting there exposed to the atmosphere, and there's still heat loss by conduction, right? I guess the moral of the story I'm trying to say is, in a scenario, there can be more than one heat loss mechanism going on, right? So in this penguin, you have heat loss by convection because air particles from the wind brushes across the flipper's surface and therefore carries with it some energy. At the same time, the penguin is just, say, standing there. So there should also be some heat transfer by conduction between the penguin's body and the surrounding air particles that are quite stationary. Tomorrow, we will learn that there is also heat loss by radiation by the penguin, and we will look at radiation tomorrow. So, but in this particular example, we're just wanting to find the rate of heat loss specifically by convection. Right. In which case, it's a direct application of the equation because we've identified everything that's given. Q is given 0.03 area. It's the area of the flippers because we're only after the heat loss through the flippers and the temperature difference. Okay. Right. So you have 35 degrees Celsius minus 20 degrees Celsius gives you 55 Celsius, which is equal to 55 Kelvin. So even if the convective heat transfer coefficient gives us temperature in Kelvin, we can safely use the temperature difference in Celsius as the Kelvin change in temperature as well. I mean, difference in temperature. So every second, the penguin will lose 0.0825 joules of energy through its flippers. Yeah.
If it's losing energy, would you expect the watt output to be negative? Your answers to be negative?
Yes. Yes. So technically, you'll have a negative Q. This is heat loss. But yeah, I think I mentioned this yesterday. Usually, the easiest will be to take the absolute value of delta T for your calculations, and then use the context of the problem to say whether it's a heat loss or heat gain. Yeah. If you want to be strict about it, though, then you can do the minus 20 minus 35, and that will give you a negative.
Yeah, I would have thought the 35 would be like it's an initial.
Yeah, except that it's not initial minus final, but it's the temperature difference, hot minus cold. Yeah.
If you wanted to work out the total heat loss, like through that's just through convection.
Yes,
If you wanted to work out conduction as well, would it be as simple as adding the two equations together?
exactly. So yeah, you have to add in how much heat is lost by convection, plus how much heat is lost by conduction, plus if there's heat loss by radiation, plus heat loss by radiation as well. So if there are more than one heat transfer mechanisms present, the total heat loss will be the sum of all of this. And the resulting change in temperature will also come from the total heat
Well, I
loss.
guess it's one of those things that's true at any given time, but it's never going to be constant.
All
because
throughout,
The
yes.
environment is always changing.
That's true. Yeah, yeah. That's why we're just looking at a small amount, yeah, small time interval. Yeah, that's right. Cool. All right, any more questions? This is probably one of the shortest lectures that we have. So that ends our lecture on conduction and convection. If there are no questions, tomorrow we will learn about radiation. Have a good day, everyone.
Sorry, I was like, my dog's